Any questions from last time on balancing equations or types of reactions? We're going to go over the types of reactions again today. We'll go a little bit deeper. How are we feeling with balancing equations? Okay. If you don't feel good about it, keep practicing. All right. Let's start with oxidation reduction. All right. So atoms that gain electrons, this is called oxidation or reduction? Reduction. So just remember the opposite of what we think. What does it reduce in? A reduction of charge. We gain electrons, our charge goes down, or negative. Good? And then atoms that lose electrons, this is called oxidation. And how can we remember this? Oil rig. Good? So oxidation reduction is when we have a transfer of electrons. We okay so far? We kind of just talked about that last time. That's not new. It's review. Do you remember when we talked about oxidation reduction reactions last time? Why we call it oxidation reduction? Well, let's do a demonstration. Anybody would know what I have in this bottle?
Nothing.
Oxygen. Air, but oxygen is necessary. Then I'm going to put some rubbing alcohol in here. Why not? Spreading it out to evaporate the rubbing alcohol. Because alcohol is what? Flammable, right? Should we turn the light off?
Yeah.
This is gonna be too scary. You gotta just hold the bottom of the switch for a while. You gotta do the other side too.
All the way?
Yeah, that's good. We got a little bit of light here. Oh, that's weird.
Oh.
A little bit of physics for you too. All right, will you turn that light off? Product is carbon dioxide and water, right? Okay. What kind of reaction is that? Besides oxidation reduction?
Combustion.
Combustion reaction, right? Carbon hydrogen compound. Like, let's write it on the board here. We have C3H8O. There's a carbon hydrogen compound with oxygen and oxygen gas. And what do we create every time? Carbon dioxide and water. Yeah. Does it matter what order we write it? No, it doesn't. Okay. All right, so that's one type of oxidation reduction reaction.
What's that smell?
Isopropyl alcohol.
Oh.
But it's not straight isopropyl alcohol. There's carbon dioxide. Okay. So we call this oxidation reduction reaction because we take metal. Here's some magnesium metal. And what happens to magnesium in the presence of oxygen? It oxidizes, right? The metal is oxidized and the oxygen is reduced. But we'll write it on the board a little bit. So we did another oxidation reduction reaction earlier this semester through sodium in water, and we get sodium hydroxide and hydrogen gas, yeah? So that is a single replacement reaction, but it's also an oxidation reduction. This is a property, a similar, all of the elements in group 2 have similar properties to magnesium, right? And this is what they are, what it is. Oh, I don't want that one. Need more fiber, more heat. Woo-hoo! You don't have to look directly at it to see the wonderfulness, right? Uh-oh,
Yeah.
we'll be fine. What's that white stuff?
Magnesium oxide.
Magnesium oxide, that's like rust for magnesium. Okay. Now, do we have to heat it to make it oxidize? No, it just goes faster, okay? But you get other elements in group 2, and it'll react similarly. Kinda cool, right? No? We should not do this stuff anymore? Okay. Alright. So, we have magnesium plus oxygen gives us MgO. Hold on, is that a combustion reaction? It has oxygen in there. Are we burning it? We're not.
It's oxidizing.
It's oxidizing. If we burn it, we're going to get carbon dioxide and water. Well, maybe not. Okay. So we start with this metal, and what's the charge of magnesium metal by itself? 0. And what's the charge of oxygen by itself?
0.
Yeah, you ever get shocked when you breathe oxygen? No. And in magnesium oxide, it's 2 plus and 2 minus. You with me?
Yeah.
Okay. So what happens to magnesium? It's oxidized. Right? We saw that it oxidized, and it became magnesium oxide. And oxygen does what? Reduced. It goes from 0 to -2. If you have oxidized, you have reduction. If you have reduction, you have oxidation. Good? So this is kind of what we did last time a little bit, just showed you this much, yeah? And Does it have to have oxygen in order for it to be an oxidation reduction reaction? No, it doesn't. So this is where we coined the phrase oxidation reduction, right? Because maybe not with magnesium, maybe with iron, right? So that's cool, but for ionic compounds, it's pretty straightforward. We all kind of made sense of what I did there, did we? I started with 0 charge, and we ended up with a charge, okay? But what about for that, this one right here? Can you guys tell me what the charge of those things are? It's not, there's no ionic compounds in there. So there's no charge, right? So we can't really do anything else until we learn about oxidation numbers or oxidation state. So the first two, we should be straightforward on how to determine the oxidation number for an element or for an atom. Okay, the first point is for neutral elements, all alone, the oxidation number is equal to 0, kind of like we did here, right? So oxidation state or oxidation number doesn't mean the charge. When we're dealing with ionic compounds, it's the same thing as the charge, okay? And that's our next point, is for ions in ionic compounds. Whoa. The oxidation number is equal to the charge of the ion. Pretty straightforward so far? How are we feeling? Okay, that's kind of what we demonstrated just barely with magnesium and oxygen. And here's one more that kind of makes sense, I hope. If it doesn't, we can talk about it. The sum of the oxidation numbers in a compound is equal to the charge of that compound.
Can you?
Talk about it? Uh-huh. So what's the charge of most compounds? 0. Are there any compounds that have a charge? Now, what do we call these? Polyatomic ions, right? Okay. So, for example, we just dealt with magnesium and oxygen bonded together. What's the charge of that compound? It's 0 because it's an ionic compound. They're all neutral, right? If we add +2, how many +2 ions are there in this compound? Just one. How many -2 ions are in this compound? One of each, so that's +2, -2 make 0. The sum of the oxidation numbers is equal to the charge of our compound. You with me? Any questions on that?
The sum of that, I'm sorry, can you repeat it again? The sum of that gives.
Yeah, so the oxidation number for magnesium is +2. And there's only one of them, so it's +2. Plus, the oxidation number for oxygen is -2. We add those together and we get 0, which is the charge of this compound. Good? So it's straightforward with ionic compounds. But for covalent, it's going to be a little bit different, right? Well, when I say different, it still follows this, but it's not as straightforward. Okay? We'll go through this. Okay, the last thing is for covalent compounds. Then we need to follow in order the following. That's weird.
Flow with the flow.
Sorry.
So with the sum of the oxidation in a compound, that one's for ions.
It's for all of them.
Okay.
Yep. But it's more straightforward for ionic compounds. Not as straightforward for covalent because covalent compounds don't have charges, right? We'll get there. But here we're not talking about the charges. We're talking about the oxidation number. Now the oxidation number for ions in an ionic compound is the charge. Okay? Here's the order. So if you have a covalent compound, you check to see if it has hydrogen. If it does, then hydrogen's oxidation number is +1. Well, it's in group 1, so it's a +1 ion. Hold on a sec. We're not talking about ions. But can you kind of make sense of it that way? Okay? So its oxidation number for hydrogen is +1. If it doesn't have hydrogen in it, we got to check, well, does the covalent compound have fluorine in it? And if it does, fluorine's oxidation number is, what do you think? -1. That's nice, right? If it doesn't have either of those, then you check oxygen, and oxygen's oxidation number would be -2. And if it doesn't have any of those, then we deal with chlorine, bromine, and iodine in that order, and they're all equal to -1. Did I say anything that was too hard yet? Maybe that part right there, right? Follow in order the following. Okay, whatever. All right, so there are all of our rules, you might call them, to determine the oxidation number for all of the atoms in compounds. Y'all have those? Okay. Let's do some examples to make sense of them all. Okay, example 1. I'm going to start easy. Calcium chloride. What is the oxidation number for calcium? In fact, first of all, what kind of compound is this? Ionic or covalent? Ionic. So how do we determine the oxidation numbers? The charge of each ion. So what's the charge of calcium? So what's the oxidation number for calcium? +2. And I usually write it right above the atom and circle it, but that's the way I do it. You can do it however you like, okay? Because this part's not the answer part, right? This is how we get there. Chlorine has an oxidation number of -1. Now let's see if the sum of the oxidation numbers adds up to the charge. What's the charge of this compound? 0. It's neutral. We have 2 -1 ions. That's a total charge of -2. And we got 1 +2 ion, total charge of +2. That's equal to 0. Good? How we feeling? Say something if you don't get something, or if you have a question, please. All right, let's do one that is a covalent compound. So really, we just talked about that one right there, right? And this one right here. Okay? So now let's talk about covalent compounds. Okay, we have carbonate, CO3 2-. This is a covalent compound, so we can't just look at the charges. We have to determine what the oxidation number is based off of this order right here. Does this compound have hydrogen in it? No. Does it have fluorine? No. Does it have oxygen? Okay. So what is the oxidation number for oxygen? -2. Oh, let me use a different color. Okay, now we got to figure out what carbon is. Okay? And we have to do this regardless if there's another one of these in there. In this case, there's not. But here's how we do it. I'm going to just draw I'm going to write an equation. And you don't have to write an equation, but I'm going to show you using an equation. You with me? Okay. So each oxygen has an oxidation number of -2. How many oxygens do we have? 3. So multiply those together and we get -6 plus whatever it is for carbon. We don't know what the oxidation number is for carbon. What is that going to equal? This is the sum of the oxidation numbers. This is equal to what? -2, because that's the charge of my compound. So I'm going to add 6 to both sides. And I get the carbon's oxidation number is +4. You with me?
No, I didn't understand very well. I'm sorry.
Okay. So let me do it without an equation.
Okay.
Maybe this will be easier. We have -2 times 3. What's that? -6. -6, and what number makes -2? Well, I just had an equation again.
Yeah, so it's basically C, okay.
Does that make sense?
Yeah, we changed CO minus, yeah.
Yeah.
We changed it to an equation.
Uh-huh.
Mhm.
Yeah.
Uh-huh.
We good?
Yes. And now where did you get the, oh yeah, because when equation -2 -6 is.
Yeah, we add 6 to both sides, and we get +4. Good?
Yeah. Thank you.
Uh-huh. Thanks for asking. Anybody else? All right. Now, we determine the oxidation number so that we can determine which element is oxidized and which one is reduced. That's why. Or to determine if it's an oxidation-reduction reaction. What's the easiest way to determine if it's an if it's not an oxidation-reduction reaction?
Convenient.
We'll get there. Did we remember from last time? Okay, that's okay. We'll get there. We'll do it again like we heard it for the first time. Okay? All right, let's do another example. So this time I'm going to start with I'm going to do a whole compound. We have sodium as a solid plus chlorine as a gas, and we get sodium chloride as a solid. Is this an oxidation reduction reaction? It's a synthesis reaction. Remember that? Okay. But what's the easiest way to tell if it's an oxidation reduction reaction? It's not a double replacement reaction. You remember that? We'll go through that again. Okay, we'll get there. But this is not a double replacement reaction, so most likely it's oxidation reduction. Most likely. How do we know for sure? We check the oxidation numbers. What's the oxidation number for sodium as a metal? 0. It's an element by itself. You with me? What's the oxidation number for chlorine gas?
0.
Also 0. Hold on to that. That's not by itself, is it? No other element. That's a diatomic molecule, right? That's how it appears by itself. Okay? And this is what type of compound? Sodium chloride. What kind of compound is this? Ionic because metal and non-metal, right? Do we still know this? We need to. Okay. So we just take the charges to be the oxidation number. What's the charge of sodium? +1. Do we have to memorize this? No, we look at the periodic table. What about chlorine? -1. Do those add to 0? There's one of each, they add to 0, so okay, that follows all of our rules. Okay. Now, I like to ask, which one is reduced? Which one is lowers in charge?
Chlorine.
Chlorine goes from 0 to 1, or to -1. So that one is reduced. Or you can remember that reduction is a gain of electrons. If we gain electrons, it becomes negative, right? Either way works. Whatever clicks in your brain. If we have reduction, we must have oxidation. That must be sodium is oxidized. We good?
I have a question.
Yes.
With the CO32, the oxidation level or oxidation number would be the -2, right?
The oxidation number, you have to do it for each element. The charge of this compound is -2. And so the sum of the oxidation numbers has to equal -2. But in this case, there's 3 oxygens. We have to count -2 3 times. Good? Okay. All right, I'm going to say one more thing right here. So we know that sodium is oxidized, right? Because it loses electrons. Remember oil rig? Okay. What causes sodium to be oxidized? Chlorine did, right? So turns out that chlorine is the oxidizing agent. You guys ever buy a home or buy a car or buy, you call it an agent, right? Do they get the home? No, they're causing you to have a home. They're the agent. So chlorine isn't oxidized. It's causing sodium to be oxidized. You get that? It's just words, guys. Okay? So chlorine is reduced. Therefore, sodium is what? Reducing agent. It's causing chlorine to be reduced. You with me? And the only reason I bring this up is so that when you read about it, you know what it's talking about. Okay? Is it on the test? You might find out on that study guide that I gave you last time. Okay? The only reason I say that is because I don't remember. We good? All right, let's do another example. KOH breaks down into K2O and H2O. Is this an oxidation reduction reaction? Looks like it because it's not a double replacement reaction. And we'll talk about double replacement reactions again if it's not clicking. We will.
Are you able to put one of each one next to each other so I can see the difference?
Between oxidation and,
I'm just having a hard time spotting it right off the bat.
okay. So remember last time we talked about oxidation reduction reaction was a synthesis reaction. That's this one right here, where we have two components making one product. That's a synthesis reaction.
Oh, okay.
And another one is the opposite of that, decomposition. We have one product and it breaks down into two components.
Okay.
And there's one more, or two more. One's the combustion reaction we did right here. Right here. We start with a carbon-hydrogen compound, we burn it in oxygen, and we get carbon dioxide and water. So those three are three types of oxidation reduction reactions. And the fourth type is where we have a single replacement. And that's when we have something like sodium, a single element, with water, or a compound, and they swap partners and it becomes sodium hydroxide and water. They don't swap partners, but sodium knocks off the hydrogen. Okay. But this one looks like a decomposition, so it looks like oxidation reduction reaction. So let's see if it really is by determining the oxidation numbers. All right. Potassium hydroxide is an ionic or covalent compound? What kind of element is potassium? It's a metal. Do you know how to determine where the metals are, guys? Remember that?
Yeah.
We need to. Okay, we need to be able to determine, differentiate between ionic and covalent compounds for the rest of forever in this class. Okay? So this is an ionic compound. Therefore, the oxidation number of potassium is, there it is. +1. Good? The rest of it Hydroxide is a polyatomic ion, and polyatomic ions are covalent compounds. Okay, so we have two of them there. We got to start with oxygen or hydrogen. Hydrogen oxidation number is also +1. You with me? Now, what does the sum of the oxidation numbers of this compound have to equal? 0, because it's neutral. Y'all with me? So +1 and +1 make +2. So what does oxygen have to be? -2. Oh, but didn't we already know that? No. We have to check. Sometimes oxygen's oxidation number is not -2. Okay, you have to check. Is it hard to check? It's not. All right, we'll go through it and make sure it's not. Okay? I'm sorry. All right, so let's do K2O. What kind of compound is this? Has potassium in it again. It's ionic, right? And this time it doesn't have a polyatomic ion, so we're just going to, whatever the charges are, done. What's the oxidation number for potassium? +1. What is it for oxygen? -2. Do they add up to 0? Yeah, because there's 2 potassiums, 2 positive ones. That makes +2, and a -2 makes 0. Good? Now for water, this is covalent. What do we do with first? Hydrogen or oxygen? Hydrogen oxidation number is +1. And there's 2 of them. That's +2. And the total charge of water is 0. So what does oxygen have to be? Was that easier? Okay, perfect. Could you write an equation?
Sure.
Yeah. So normally I don't write an equation if it's simple like this, but I definitely can. And if it's a complex compound, I most of the time will. Okay? All right, so which one is reduced, guys? Which one lowers in charge? Which one gains electrons? There's only 3 atoms here, 3 different elements. What happens to the charge, the oxidation number for potassium? From here to here? Oh, it stays the same. What about from oxygen? Same. Hydrogen? Is this an oxidation reduction reaction? No. You with me? So the reason I show this one is so that you know, okay, you think you might know it's oxidation reduction, but you got to check. Okay, that's why we're learning oxidation numbers. Okay?
So this is still a decomposition, but not redox?
That's right. But for the most part, guys, if it's not a double replacement reaction, your best guess is oxidation reduction, but then you got to check. Okay? Another one? Okay. Example 5. SO2 plus oxygen gives us SO3. This time we don't have any ionic compounds, but this is a synthesis reaction, so most likely it's an oxidation reduction, right? Let's check. So SO2, which one do we deal with first? Sulfur or oxygen? Oxygen, because it's a covalent compound, right? So this is -2. There's 2 of them, that's -4 total. You with me? So what does sulfur's oxidation number have to be? +4. Are we doing okay? Anybody have a question so far? What's the oxidation number of oxygen in O2? 0. Because it's all alone. Now we go to SO3. What do we deal with first? Sulfur, oxygen. Oxygen is -2. There's 3 of them, that's -6. So what does sulfur have to be? +6. All right, which one is reduced? Oxygen goes from 0 to -2. What about that oxygen? It doesn't change. But that's not what we're interested in. What does change? Okay? So this oxygen goes from 0. This oxygen is -2. So this one is reduced. Which one is oxidized? Sulfur. Because it loses electrons.
The other one gain,
Mm-hmm.
that's why it's reduced,
Yeah.
and then, yeah, it's like everything's backwards.
Well, I like to think of it, so I don't have to think of backwards, is oxygen goes from 0 to -2. The charge is reduced. Good. That's what I like to think.
Yeah.
Because I remember learning this in general chemistry a long time ago. And when they brought this up, it's like, holy crap, that doesn't make any sense. Doesn't make any sense. But can you make sense of it through the charge? The charge is reduced. And oxygen is oxidizes the other one.
How do you know we should determine oxygen first in SO2?
Because SO2 is a covalent compound, and in our rules, when it's covalent compound, we have to follow this in this order. It didn't have hydrogen, didn't have fluorine, but it does have oxygen. And oxygen's oxidation number is -2. You with me? That's how I know. And who made these rules up? Men or women. Okay? People did. And why do we make rules? To help us to remember something.
Brainwashing.
Yeah, basically what we're doing. If you want me to brainwash, I'll talk to you. No, I'm just kidding. Okay. How are we feeling? Do we need any more?
Yeah.
Okay, let's do one more. Let's do C3H8. So that's propane plus oxygen. What does it give us, guys? Can you predict this? You should be able to.
Carbon dioxide.
Carbon dioxide and water. This is a combustion reaction. Can we all recognize those? Okay? All right. So let's break it apart. We have only covalent compounds, so we have to follow the covalent compound rule. Which one do we deal with first, carbon or hydrogen? Hydrogen has an oxidation number of +1. +1 times 8 is
8.
+8. +8. And there's 3 carbons. And what's the total charge of this compound?
8.
What's the total charge of this compound, C3H8? How do you know? You look right there. What number is that? Oh, there's not one. If there's no number, no sign, it's neutral. You with me? So the charge is 0. Then we're going to subtract 8 to both sides. And we got 3x is equal to negative 8. Divide 3. Hold on. Can we do negative 8 divided by 3 and get a whole number? No, but it's okay. It's okay. No big deal. Negative 8 thirds. That's it. Well, let me write it with a different color. Stay out. Oh, I'm sorry. I mean, you can come in. Okay. So that's the oxidation number for carbon here. But guys, that's not its charge. No big deal. This is just an oxidation number. What's the oxidation number for oxygen in O2? 0. Where do we start with in carbon dioxide? Oxygen, good. No, you're good. Oxygen. Oxygen's oxidation number is? -2. There's 2 of them, so that's a total of? -4, so that means carbon has to be +4. And water, we just did it a couple of times already. +1 for hydrogen, there's 2 of them, that's +2. This has to be -2.
Why oxygen then?
In this one,
Why?
we go back to our rule. This is a covalent compound, we got to go in this order. There's no hydrogen, no fluorine, but there is an oxygen. That's why.
Just why 0?
Well, that's why it's 0.
Yeah, why it's 0 in there?
Why is the charge?
Why the charge is 0 there?
Oh, okay. Because what number is right there? No number. Its charge is 0. Most of the time it is going to be 0. In fact, almost 100% of the time, guys. Because normally we don't deal with reactions with just polyatomic ions. Okay? All right. Are we good with this one? Now let's determine which one is reduced. Which one lowers in charge? Oxygen goes from 0 to -2 right there or right there. Doesn't matter. You don't have to do both, just one of them. So that is reduced. Reduced. And carbon, what happens to carbon? It goes up. It's oxidized. Do we care what that number is? No, it's a negative number going to a positive number. Good? So which one is the reducing agent? Carbon.
Carbon is,
Yeah. We good?
it's almost like,
Yeah, it's just flip-flop. Okay? How are we feeling? Okay? So the worksheet that I gave you last time has practice. Do we need to do another practice, or how you feeling? Do you want to practice or do you want to move on? Whether you practice now or later, you need to practice sometime. What do you want to do?
Practice 1.
Practice? Okay.
Should we do something in the worksheet?
Yeah, let's do it. Anybody need one? Did you get?
I didn't get the study guide either. Thank you.
What? Yeah. I thought you said 2 of them.
Oh, no,
Okay.
thank you.
Thank you.
Thank you.
All right, so page 1 was from last time. The first side was from last time. Second side is assign oxidation numbers to each of the following and determine which one is oxidized, which one is reduced. So section 3. Do you want to do it on your own? I would. Need one? Did you get her? Did you get her study guide?
Yes,
Okay.
for the last time, right?
Uh-huh.
Yeah, I just didn't remember.
Yeah. You okay?
Yeah, it's just like a V, just.
A bee.
I've had
Yeah.
that before. I think they die
Yeah.
on things and they fall down. It's awful. I thought they were falling into my hair.
She was stuck in my head, and I was like, what?
Happy Halloween.
So that's why you gotta check. Not just because they said so. So do you know like why they, when they came up with the rules, how they figured out like the charges?
The oxidation numbers?
Yeah, for the covalent, like what you gotta check for?
I didn't talk about that. Should have. When everybody's with me, I'll tell you. I'll tell you my thought. I don't know if this is the real thing, but I'll just tell you my thought.
Gotcha. That's better than no thoughts.
Yeah.
You need lots of stuff to connect everything.
Yeah. I did last class. I spaced it this time.
It's getting late. Hey, Thursday, we're gonna have to see you Thursday.
Oh, you're happy about that, huh?
Is H2O2 hydrogen peroxide?
Mm-hmm. one more.
Oxygen is reduced.
Which one's reducing agent?
See, what's funny is determining the noun of which one's which was a lot harder for me than just the verb, which one's what's happening to this one
Yeah,
versus which one is this.
yeah.
So I have to do the verb first, then think about the noun. I actually have to think about it.
How are we feeling? Do we have any questions? If there's not any questions, I'd like to move on.
Can you do one that I was having a hard time with?
Yeah, which one?
It was H2O2,
Mm-hmm.
H2O plus O2.
Yeah. So let's go ahead and start this. These are all covalent compounds. So we start with hydrogen first is +1. There's 2 of them. That's +2. +2 plus 2 oxygens has to equal what? 0. So we -2 to both sides, divide 2. It's -1. You see, oxygen doesn't have to be -2. And then we do water. We kind of already did this a million times. Uh-oh.
Wait, hydrogen is not
Oh my gosh.
+1?
Yes, it is.
Okay.
So which one is oxidized? Or which one is reduced, I like to start with? Which one is lowered?
Oxygen is reduced.
Oxygen goes from -1 to -2. So that's reduced. Which one is oxidized? Oh my gosh.
In Mopar?
Yes. Good? Anything else? Okay, let's move on. To precipitation reactions. So let's talk about double replacement reactions real first. So, for example, we have, sodium chloride with silver nitrate. And when we have a double replacement reaction, did I say that weird? Double replacement reaction, okay. Sounded weird in my head. They must be aqueous solutions. Do you remember this? So we have two ionic compounds that are in aqueous solutions. What does aqueous mean?
Water.
It's dissolved in water. Okay? And then what we get is the cations swap partners. So sodium hooks up with nitrate. To know the formula, sodium is 1 plus, nitrate is 1 minus. You cross the charges and you simplify, and you get NaNO3. Y'all remember this? And it turns out that one is aqueous. And then silver hooks up with chlorine. What's the charge of silver?
+1.
And if you don't remember, you figure it out, right? Nitrate is 1 minus, and how many nitrates are there, guys? How many are there? 1, because no parentheses, right? So this side has to be +1, and there's only 1 silver, so it is a +1. So silver's +1, chlorine is -1. It's a 1-to-1 ratio. We get AgCl. And it turns out that that's a solid. We'll talk about how we know that, but not yet. That is an example of a double replacement reaction, because two things are being replaced. Good? If we have a double replacement reaction, it will never be an oxidation reduction. So if we can recognize that, we don't have to worry about oxidation numbers. Get that down, okay? All right, there are two types of double replacement reactions. We got precipitation reactions and acid-base. So let me show you an example of each. Here I have lead nitrate. What does it look like?
Liquid clear.
Clear, water.
Water. It looks like water. It's an aqueous solution of lead nitrate. Oh, just have to get enough so that I can actually see something here. Here's a aqueous solution of potassium iodide. It also looks like water, right? And here, watch what happens when I mix them.
Change color.
It doesn't just change colors.
Does it become solid?
It looks like cloudy, right?
Yeah.
And what do we know is happening when we have clouds in the sky? Precipitation, right? Okay. All right, I don't know if that's why. Okay. So that yellow stuff turns out is a solid. It does not dissolve in water. When we get that yellow stuff, we call it a precipitate. It's when a solid forms from mixing two aqueous solutions. And that's how we know it's a precipitation reaction. Good? You can kind of see yellow on the side there, right?
Yeah.
Those solid particles. And you kind of see this yellow stuff sinking at the bottom, right?
Yeah.
Maybe not from where you're sitting. Let's put this somewhere. What? Do you want to the whole time? That'd be weird. It might take a while. So I'm gonna, let's see if I can prop it up here. All right, so that is precipitation reaction. When a solid forms, Now let's do acid base. Now, I forgot to bring safety goggles. Are you guys gonna turn me in? We're
Yeah.
dealing with acids and bases here. In my last class, someone had safety goggles.
Wow.
Oh, look at that. These are cool.
There you go.
It's like you're going to Burning Man.
Okay. So here I have an acid, hydrochloric acid. And here's a base, sodium hydroxide. And we can't tell what's happening because these are liquid water solutions, right? Aqueous solutions. And if I just dumped them in, we wouldn't see anything. So I have a acid-base indicator. Probably overkill, but alright. Yeah, let's just do a little bit here. So if you get hydrochloric acid in your eye, a high concentration, you could go blind. If you get sodium hydroxide in your eyes at high concentrations, you could also go blind. You put them together in the right proportions, you can drink it. So once we're done here, I'm gonna ask for volunteers. No, do not try this at home, ladies and gents. How often are we perfect? Well, if you're talking about me. Okay, I'm just teasing. Alright. And do you guys do this titration lab yet?
No.
Some of us are saying, yeah, okay. Well, this is kind of like a titration lab here. So we're gonna put it in there until it neutralizes. And how we know it neutralizes, it's light pink. Okay?
Oh.
So we can see the pink there, right? And as we put more of this stuff in there, the pink lingers longer. That means we're getting closer. And if we get too impatient, we went too far, and we gotta start over again. And the whole purpose of this is so we can predict the concentration of an acid or a base. Getting longer. Ooh. And in the lab, you have a stirring rod, right, that kind of stirs it for you. Ooh, did I go too fast? Okay, we're good. You all see that? Sorry, I'm a short guy here.
Wow.
Ooh, that might be it. Ooh, that's it. Okay. My last class, we overkilled it by one drop. Okay, so that's pretty good. No, I'm not gonna do that. And I'm not gonna let you do it. Alright. But, in theory, we should be able to drink this. Well, it has this garbage in it, but sodium chloride and water, that's it. Pretty cool, right?
They do grab your glasses.
You want some glasses? Thank you, appreciate it. Of course. Oh, it's turning darker. How do we get it to be white again? Put a little bit more acid in, right? Can you see that yellow solid at the bottom? I can. Oh, sorry. So that's acid base and precipitation reaction. We good? Pretty much pros now, right? Okay. So if it's a double replacement reaction, these are our two options. If it's not, then it's most likely oxidation reduction. All right. So let's write this down. A precipitate is a solid forming from two aqueous solutions. So let's write that equation down that we just saw with the precipitation reaction. So we had lead 2 nitrate in aqueous form, potassium iodide, aqueous solution, and this is a double replacement reaction, so the potassium hooks up with nitrate and becomes potassium nitrate, one of each because they're both 1 plus and 1 minus charge across the charges, and lead 2 plus, and if you don't know what it is, you figure it out, right? And iodine across the charges becomes PbI2. And it turns out that is the solid. And that means potassium nitrate is aqueous. And this is how you know it's a precipitation reaction. We good? Now I'm going to show you how you figure this out without going to the lab. Because you're going to have to do that on the exam, right? So I'm going to give you...
Walk in with these? To the testing center?
Yeah, with all of them, because you don't know which one is on the test. Right? Okay, so I'm going to give you a soluble ion chart. What does soluble mean?
Dissolved in water.
Means it dissolves in water. It doesn't have to be water, but water is the universal solvent. And over on the right side of this table, we're going to have exceptions. Oh, gosh. Exceptions again. All right, so the first one are group 1 ions. And that's like H plus, Li plus, Na plus, etc. All of them. If a compound has a group 1 metal in it, or hydrogen ion, then it is soluble with no exceptions. Woohoo, we like that. Okay? So you're going to have to look at the compound and see, does it have a group 1 ion in it? If it does, it's soluble. And how do we write that it's soluble? We write AQ in parentheses. Okay? The next set of ions are polyatomic ions, not all of them. I'm going to write down which ones. So we got ammonium ion, NH4 plus, nitrate ion, NO3 minus, perchlorate, ClO3 minus, ClO4 minus, and acetate, which is C2H3O2 minus. These guys are soluble with no exceptions. Good? Two more. So this really isn't a whole lot, but you do have to memorize this. Okay? So if it's halogen ions, do you guys remember the halogens? Group 17 on our periodic table. But in specifically, the chloride ion, bromine ion, and iodide ion. Why didn't I use fluorine? Because it's only slightly soluble. All right, so just these three. But these do have exceptions. These guys are soluble for the most part, except when bonded with silver plus, lead 2+, and that's it. Well, there is one more, but we never use it, so I'm not going to give it to you. Good enough, or do you want it?
Thanks.
Give it to us, please, give it to us. Okay. And then the last one is sulfate, SO4 2-. These are soluble except with lead 2+, same as that one, but not silver. And two more, strontium 2+ and barium 2+. Where are strontium and barium on the periodic table? On the bottom of the second column, second group. These are the heavy second group 2 ions. If you want to remember it that way. Okay? And guys, we are keeping it simple here. I can give you a whole nother chart for insoluble ions, should I? Or we can just say, if it's not on this chart, we can assume that it is insoluble, meaning doesn't dissolve in water. Good enough?
So they don't ask about mercury?
That's the one that we never use.
Don't make it complicated.
But yeah,
Just in the book they mention it, so.
yeah, mercury 2+ is the other exception for here and for here.
Okay.
But we could just leave it like that.
Sorry, you said if it's on the list, we can assume what?
If it's not on here, then we can assume that it's insoluble. That means it doesn't dissolve in water. So what happens if chlorine is bonded to Pb2+? Or, for example, iodine is bonded to Pb2+. We just did that one. It's not soluble. It's insoluble. That's the yellow stuff. Good? So those exceptions means it's insoluble. Good? All right, let's do some practice problems or examples. Does anybody need or do we all have that? Okay, because we need to have that in our brain. Okay, example 1, we have NH4NO3. Soluble or insoluble?
Do we need to remember this table?
Yes. What do you think? Soluble or insoluble?
Soluble.
Soluble because of both ions. There's no exceptions on either of those, right? So how do we mark that it's soluble? AQ. That means it's soluble. We good? Okay, another example. Lithium hydroxide. Soluble or insoluble? Soluble because of lithium is a group 1 ion. So we say that it's aqueous. We okay so far? Next one is PbCl2. What is it? That's insoluble because chlorine is insoluble with those exceptions. Normally it's soluble, but it has Pb2+. So how do we mark that it's insoluble? A solid, just like we saw in the example, right? In the experiment. So that's insoluble. Then example 4 is FeOH3, iron 3 hydroxide. Soluble or insoluble? It's not on our chart, therefore we assume it is insoluble. So it's a solid. You with me? There's not iron on there, there's not hydroxide on there. You okay with this? It's not a whole lot on that chart, but you do have to remember it.
Do you have any tips on how to remember that?
Oh, I was going to talk about one other thing too. So yeah. On the polyatomic ions, you're just going to have to remember them. There's 4 of them. But the main group elements, so like the alkali metals, those guys are the most reactive, right? I don't know if this is why, but they're reactive, so they are soluble. The halogens are reactive, they're soluble. There are a couple of exceptions, because the halogens are the most reactive nonmetals. Alkali metals are the most reactive metals. That's kind of how I remember it, but is it pretty straight with no cracks? No, it's not. Okay, I'm going to go back up here to these rules up here. How do we know just these ones right here? These are the diatomic molecules, except for nitrogen. Remember diatomic molecules? These are, and also they're the most, so these ones right here, so fluorine, they're kind of the higher in electronegativity value too.
Oh, is this the 7? Maybe 7.
Yeah.
Okay.
These aren't the 7, but this is only 6 of them, right? Yeah, but yeah. So just maybe to help you to remember which ones they are, and in order of highest electronegativity, except for hydrogen, because it's the king of exceptions. We do it first. Okay, how are we feeling? Okay, you ready to do an example like you'll see it on the test? Okay, we're going to have a full equation here. So we have silver nitrate in aqueous solution plus sodium chloride, also aqueous solution. And this is a double replacement reaction, so we're going to get silver chloride. Ooh, gonna die. battery's getting bad because it used to hold a full charge. And then what else do we get? Sodium nitrate, good. All right, so is any of those insoluble? Are they both insoluble, or is one of them soluble? Or are both of them soluble, or is one insoluble? Which one is insoluble?
Silver chloride.
Silver chloride. So we're going to put an S right there. And this one right here is soluble, so we're going to put AQ. You with me? Is this a precipitation reaction?
Yeah,
How do we know?
a solid.
We get a solid out of two aqueous solutions. We good? Now let's talk about what is happening here. Okay, we saw the demonstration, but that's kind of, we can't see what's going on microscopically. So here we go. We have a container of water, and we throw silver nitrate in it. Does it dissolve? How do we know it does? It's aqueous, right? And what happens to salt when it dissolves? It dissociates. It splits into its ions. You remember this? Or if you don't, no big deal, but you need to know it now. Silver splits into Ag plus, and silver nitrate splits into Ag plus and NO3 minus. You with me? Does sodium chloride split? Yes, because it's aqueous. It's soluble. So sodium splits up with chlorine. We good? And what happens? These two come together. Why? Well, these are opposites too. Not quite, but good. Because silver and chlorine are insoluble. So they come together and clump up into solid. Does sodium and nitrate come together? No. It's still aqueous. It stays dissociated. You with me? So, how do we write that on our paper? Do you want to draw this picture every time? Maybe not. So we're going to write the complete ionic equation. So this guy right here, we know does split, right? Because it's aqueous. So we're going to get Ag plus nitrate, NO3 minus. You with me? Sodium chloride also splits because it's aqueous. We're going to add to that Na plus and add to that Cl minus. You with me so far? Does AgCl as a solid split? No, because it's insoluble. It's a solid. So we're going to just write that as is. AgCl as a solid. Does sodium nitrate split?
Yes.
Yes, because it's aqueous. Na plus and NO3 minus. So there is our complete ionic equation. Now, we like to have things simple, right? Well, that just made it worse. So this is not the final product, the final end result. So we got to find the spectator ions. You guys know what a spectator is?
Not involved.
Yeah, somebody that's not involved. Now, they think it's their team, but they say, it's my team, right? But well, they have nothing to do with who wins and loses, right? I cheered really loud. It was me. Okay. Maybe, but okay. So spectator ions are the ions that do not participate in the chemical reaction. So if they don't participate, let's get rid of them. Can you see a spectator ion here? NO3 minus. How do we know that's a spectator ion? Because it's in the products as well. It did not change. So we can get rid of them. You get rid of it on one, minus on one side, minus on the other side. They go away, right? What else is a spectator ion? Na plus. It appears the same way on both sides. And what we're left with, we call the net ionic equation. After taxes are taken out. And we get Ag plus. And we're going to write AQ because it is an aqueous solution to begin with. And chloride in aqueous solution. And we get AgCl as a solid. Whew, that's pretty simple, right? Is it balanced? Then we're good. Make sure it's balanced. We good? Is there ever a chance where we have no reaction? What if we have this? NaCl plus lithium nitrate. This is aqueous. This is aqueous. And we get sodium nitrate. Is that aqueous? Yes, because it has sodium and nitrate in it. And we get lithium chloride. Is that aqueous? Yes, because lithium is a group 1 ion. What if we split this one up? They would all be spectator ions. Nothing is formed. Does this really form? No, this is a no reaction. Nothing happens. We good? Anybody want to write the complete ionic equation ever again? Then don't. Watch. I didn't say don't watch. Okay. What's my product in this reaction? I only have one. What is it?
Silver chloride.
It's my solid. That's my product. I'm going to put it in the product section. And how do we get that? We get it with silver plus and Cl minus. Because that's what makes up AgCl. Done. In the end, I'm going to ask you to write the net ionic equation, not the complete ionic equation. If it helps you, then write the complete ionic equation. Good? All right. Last thing we got to do is acid-base. Do you know how to tell if it's a precipitation reaction so far? If it forms a solid, right? It's a double replacement reaction that forms a solid. All right, so let's do the reaction we did up here in the front of class. We have hydrochloric acid. And how do we know it's an acid?
Have H.
In fact, let me write this down actually. Before I do this, sorry. So acid-base reactions. Has to have both an acid and a base. The acid is an aqueous solution that produces hydrogen ions. So if we just have HCl, for example, hydrochloric acid, if we have that all by itself with no water, it's not an acid. It has to be dissolved in water to be an acid. And it has to produce H plus ions. Good? You ever heard of solid acid? Well, maybe people take an acid. Different, okay? All right. A base is an aqueous solution producing hydroxide ions. For now. We're going to get a little bit deeper into acids in chapter 10, acids and bases. But for now, this is it. What did we call acid-base reactions last time? Neutralization reactions. Okay. Okay, so the example we did was HCl in aqueous solution plus sodium hydroxide in aqueous solution. This hydrogen is what makes it an acid. This hydroxide is what makes it a base. So you have to have that to be an acid-base reaction. And then this is a double replacement reaction, so the sodium comes over here to the chlorine and makes sodium chloride. Is that aqueous? Yes, has sodium in it. And hydrogen comes over here to the hydroxide and makes what? Water as a liquid. So here's what makes it an acid-base reaction. We start with an acid and a base. We end with salt and water. Sometimes I just want to try tasting that, but I'm scared. It'll probably just give me mean heartburn if it's not. I don't know. Does that make sense to everybody so far? All right. So, can we write the net ionic equation for this one? Should we write the complete ionic equation first? Who wants to? Okay. Then what's my product here? Water. And how do I get water?
Hydrogen and hydroxide.
H plus and OH minus. This is the acid. This is the base. And every time we have a neutralization reaction, this is what we get. Every time.
So can you call hydrogen with H plus just a proton?
Yes. For the most part, they're called protium.
Is that where proton pump inhibitor comes from? When you take an antacid?
Probably. I'm not
Oh,
professional in that area, but sounds like it. Yes. In fact, yes. How are we feeling? Can you recognize the difference between acid-base precipitation and oxidation reduction? Good. What's the easiest way to tell that it's not an oxidation reduction? Double replacement. And if it's double replacement, then it's either precipitation or acid-base. Any questions? Does anybody need another example of an acid base? Will we always get NaCl as the salt? We will not. What's another name for salt? Ionic compounds. Good. Okay, that's all I have. Any questions?
on the worksheet, under section 5, number 2, the copper sulfite,
Sulfite, yeah.
okay, so that wouldn't be soluble, right?
It looks like it.
'Cause it says oxalates, right? But it says sulfite.
That means I'm not gonna test you on that one.
That's what,
Right? I'm giving you guys the bare minimum.
okay.
Yeah, right.
I am.
I was just confused on the.
If you guys take general chemistry, you're gonna wanna jump in my class again. Okay, say, oh, let me take that class again. Promise.